Yeah.
Now that I've got that off my chest, let me get into the main body of the talk. I'll start off just by looking not backwards, but at the current state of the programme, the SMR programme and the various AMR initiatives that BEIS is funding. I think there's some useful lessons to learn looking at what's happening in the SMR programme delivery, aiming for first of a kind by 2030, looking at what that focus of a timescale does to your readiness to adopt new technology, and also sort of trying to express that in terms of its implications for AMR delivery. And I also wanted to cover some of the things that Tom Scott was referring to, which was the nuclear support to zero carbon impacts. A number of different routes forward, and I think we have to look forwards, not backwards, at historic programs if AMRs are to achieve an impact. So let me start off with the small modular reactor program, UK based, led by Rolls-Royce and those partners. Of course, there is a long established base of delivering pressurized water reactors in the UK for the submarine fleet. The key thing about the UK SMR is the use of modular construction techniques to reduce the construction cost of the asset. The timescales, the official timescales, are to achieve first of a kind by 2030 and generic design assessment approval by 2025. That, although that may seem a long way off, when you look at the critical path and work backwards, it drives a number of behaviours, and particularly that the reactor island technology will tend to be conventional. A number of innovations that you might make probably wouldn't be feasible in those timescales. Now, just look at the various technologies that BEIS funded on the first round of the UKMR. I've mentioned the SMR already there, and generally it's high temperature gas reactors, and I'll give some more detail on these in a moment. Various classes of liquid metal, molten metal cooled reactors, and then the odd one out is the molten salt reactor from Moltex Energy. I've not included tokamak on this because I'm concentrating on fission reactors. But I'm not going to go through each of these lines in detail, except perhaps to make a number of observations. The first one is the bottom row is the UK SMR, the PWR by Rolls-Royce and partners. And at 443 megawatts, actually, it's not small at all. In fact, it's almost the largest of those reactors. The key distinctive part of it is the modular construction leading to levelized cost of electricity reduction. There are then a range of very low power reactors, mainly looking for off-grid applications. And then some higher power reactors, but generally the theme is to go to higher temperature operation. The sorts of advantages that the AMRs offer support for load following, cost reduction, or provision of process heat. And they do need to provide those. If they can't provide those benefits, then there will be no incentive to move away from conventional PWR or BWR technology. So you need to consider the applications. I'll come back to this point later. The maximum temperatures stated here are around 700, 750 degrees centigrade. They may be able to go higher. They may have to go higher, and I'll explain that comment later in the talk. The current state of the BEIS programme is that this has now been reduced to, in addition to the UK SMR, the U battery project by Urenco and its supply chain, and the Westinghouse-led cooled fast reactor. BEIS is not funding Moltex Energy, but they do have a number of development activities underway in the UK at the moment. So let's just look at some observations of mine from the small modular reactor program. The first point to make is that the coolant chemistry is not conventional PWR. I'm not going to detail exactly what it is, but it is different, and it is not the same as is used in the submarine fleet either. The consequence of that relatively minor change of chemistry is that a load of issues such as stress corrosion cracking, environmental fatigue, and possibly general corrosion require the materials to be requalified in support of the program. So you don't likely change the coolant, but if you do, there's a penalty to pay for the amount of qualification work. That's particularly poignant for testing of irradiation performance of materials. So irradiation-assisted stress corrosion cracking could be a time-limiting step. If you need to do that, it's expensive and it's slow to do, and there are limited facilities to support it. There's certainly nothing in the UK. So it's preferable to avoid having to do it by a design that sticks to what is confident knowledge that can be tabled in a safety case. The position on fuel and cladding is that it is regarded as the responsibility of the fuel vendor, not of the UK SMR consortium, and that will have implications for AMRs, as I'll explain shortly. The thermal hydraulics is an area of special sort of pressure on the critical path of the program. The verification and validation of the design, particularly under accident conditions, requires tests to be undertaken to represent the circuit at full height. There isn't at the moment a suitable test facility in the UK to enable that work to be carried out. It may need to be done overseas. It may be possible to do it in the UK, but it is right on the critical path, and it implies that there are facility needs to support the SMR fleet in the future. The other point is that there are several advanced fabrication technologies that have been identified, developed by TWI, and particularly NAMRC. Electron beam welding, additive layer manufacturing, various methods for making advanced dissimilar metal welds. But they can't be adopted on the SMR program because to qualify them wouldn't be consistent with the critical path. I will mention powder metal hot isostatic press fabrications, which is an advanced fabrication technology and is being adopted. But if we translate that in terms of implications to potential AMR programs, all of the AMR designs certainly aren't conventional PWR coolant. In fact, they're far from it. All that massive database from the world's PWR reactors is not relevant to this. So it implies that whichever of those AMR technologies is chosen, there needs to be a catalogue of materials performance and understanding in the coolant at the temperature of operation of the AMR. For irradiation testing, and this chimes with what Susan was saying earlier on, we don't have an irradiation facility suitable for generating large amounts of AMR data in the UK at the moment, so it would require access to international materials irradiation data or specialised facilities. Equally, for fuel and cladding, there is an implication for an advanced fuel program, including the cladding performance, particularly the cladding performance, because that is where the interface with the coolant will be. For thermal hydraulics, again, it's been discussed that the Menai Science Park may be home for a national thermal hydraulics facility. The focus of that may need to be advanced modular reactor thermal hydraulics verification if there is an AMR program following. Otherwise, there will be key features of the flow circuit which can't be verified, and I think it needs to be part of the whole vision that the thermal hydraulics facility to support AMRs would be required. And finally, we can have ambitions for doing advanced fabrications, and when the timescales are easier, part of the advanced fabrication isn't just making the components cheaply, it's demonstrating that it's robust under the particular operating conditions that the AMR will need to operate under. Another set of comments I'm going to make is embracing the digitalisation industry 4.0, and there are a number of nuclear specific observations I'm going to make here. We've talked about R5, R6 structural integrity assessment procedures that came out of the fast reactor program are core to EDF's support of the AGRs and are world leading in many ways. But that is not the digitalized agenda. That software really needs to be embodied in software and linked to plant operating data. One issue that I'm aware of is the relap code, which I believe is made available to the UK industry through ONR. It's not actually UK owned, but its application is limited to legacy reactor designs. The agreement does not cover advanced and novel reactors, so that will need to change if relap is to be adopted or something equivalent. There are a number of diagnostic instruments that are used currently, whether it's NDE for external examination or in situ plant measurement. But there's a lot more that can be done in that space, both from instrument development and in managing data. So the vision of Internet of Things to manage fleet performance, cybersecurity and big data assessment are all areas, I think, for development. The BEIS-funded digital TWID project called NVEC has run 2 phases now. That, I think, needs to progress to the implementation of digital twins for typical reactor applications. It's not the structure and the high-level architecture is established, but the demonstrator of the benefits and incorporating digitalization in the reactor design and operation hasn't yet been achieved. And I will also mention links to ASME. On a piecemeal basis, a number of staff in the UK industry have engaged with ASME, mainly from the nuclear propulsion programme. We have an opportunity now that there is a UK-based international ASME working group to feed into ASME approval for changes to the procedures, which will be required if our AMRs are to be realised, and that is an opportunity to engage in a way which previously we haven't had. I'm going to come now to an extract from a recent NIRAB report, which shows the impact of net zero carbon by 2050. The bar chart there shows in light blue the low carbon energy in recent years, and also the fossil fuel-based power consumption that we've had. The zero carbon by 2050 doesn't just mean that you eliminate the dark blue. It also means that wider use of transport fuels and heating for domestic industrial purposes needs to become zero carbon as well. And that ultimately means that the power of the grid needs to be increased substantially. Tom referred to this earlier. And that is an opportunity for nuclear. it's not just an opportunity in terms of the electrical power output, but also the heat power. This illustrates the point. Hydrogen is an opportunity for the industry. Conventionally, you can use electricity to generate the hydrogen. However, if you contribute heat as well, for the solid oxide electrolyzer technology, the efficiency can be greatly increased. That means that the levelized cost of electricity from nuclear is substantially more competitive than currently, and that's not available for any of the renewable technologies. I'll refer to an alternative vision of the future. Rather than eliminating fossil fuels from transport, there is current technology which can derive diesel or kerosene. Starting in the middle diagram there, steam methane reforming is a conventional process. I've put the equation at the bottom by which methane can be converted to syngas, carbon monoxide and hydrogen. The other reaction that takes place is the water gas shift reaction, which is an equilibrium reaction. If you're going to make syngas, it likes to operate at about 800 degrees centigrade. That is a good target temperature for advanced modular reactors if they are to contribute to this, because that is a highly endothermic process. It wants to suck heat in. The next stage in the process is to convert syngas into long-chain hydrocarbons using the Fischer-Tropsch process. That produces long-chain hydrocarbons such as diesel and kerosene. As I'll show you in a moment, that is conventional technology. The other part of the process is where the carbon comes from, which is direct air capture. That again is a conventional process involving sodium hydroxide and calcium hydroxide scrubbing, and that feeds into the steam methane reforming reactor. So overall, what you're doing is taking carbon dioxide and forming it into long-chain hydrocarbons with the input of energy, electrical and thermal. If you think that's fanciful, most of those technologies already exist. This is the largest gas to liquid plant in the world at the moment, the Pearl plant, owned by Shell in Qatar. It produces 260,000 barrels per day of oil, which is 6.5% of Shell's production. The great advantage of this approach is that there doesn't need to be any upgrade of Rolls-Royce's aero engines or any other transport system that we use. The overall process is net zero carbon because the carbon is recycled from the atmosphere. I'll close just by summarizing these points. First of all, it's to urge a focus on the critical path items that have influenced the SMR program. If we're to implement an AMR program, those things need to be thought about and addressed. And the time to start addressing them is now, if we're serious about mid-2030s implementation of AMRs. The other point I'm going to make when I close is that it's not sufficient just to focus on the nuclear plant. You need to focus on why the AMRs are being used. It's part of an overall industrial process. If we're saying that nuclear can contribute heat or load following, then the front-end engineering design studies that demonstrate that and show the viability of it need to be in place. If we can't demonstrate those things, then there's no point embarking on an AMR program. With that, I'll stop sharing and hand over.
Many thanks, John. That was rather nice, if not a focusing presentation for us.